We're in section 8.2 and we're looking at semiconductor theory. And we're starting out with a discussion of intrinsic semiconductors. Silicon, germanium, and gallium arsenide are primary materials used in semiconductor devices. Silicon and germanium are elements and are intrinsic semiconductors. In pure form, silicon and germanium do not exhibit the characteristics needed for practical solid-state devices. Isolated semiconductor atoms. Silicon and germanium are electrically neutral. That is, each has the same number of orbiting electrons as protons. So there is neither negative or positive. They are neutral. Both silicon and germanium have 4 valence band electrons and so are referred to as tetravalent atoms. This is an important characteristic of semiconductor atoms. You may recall from chapter 1, we talked basically about this concept. Remember, we had a conductor, and we talked about things like gold, silver, copper, and their characteristic that we noted was that they had only 1 valence electron, so that it could be easily dislodged, and this would support current flow. And then we looked at other devices, or not other devices, but other materials. We called it an insulator. And this material, the characteristic of an insulator, was that it had 8 electrons in the outer valence shell, and this made it very stable and so that it wasn't subject to chemical reactions. Materials like glass, ceramic, these are materials that have 8 electrons in their outer valence shell. Now, we're in the subject of semiconductors now, and semiconductors have the unique property of having 4 electrons in their outer valence shell. This will make them suitable for some very unique processes. Well, they're not in their base form. They won't be suitable, but we're going to be able to modify them so we can do a lot of things with them. Okay, semiconductor crystals. Tetravalent atoms such as silicon, gallium arsenide, and germanium bond together to form a crystal or crystal lattice. Because of the crystalline structure of semiconductor materials, valence electrons are shared between atoms. This sharing of valence electrons is called covalent bonding. Covalent bonding makes it more difficult for materials to move their electrons into the conduction band. And here we see this lattice structure that is referred to in reference to tetravalent atoms. Tetravalent atoms bond to form a crystal lattice. The picture shown shows a one-dimensional view. Each atom has 4 valence electrons. In the outer ring, they share 4 atoms with other atoms for a total of 8 valence electrons. This creates a very stable, tightly bound structure. The shared electrons are referred to as covalent bonds. And so here, this is one of the silicon atoms, and it has 4 electrons in its valence shell. And what's happening here is you're seeing that there are 8 in its outer shell. Now, the reason there are 8 is because it is sharing an atom with one of the other atoms that is right next to it. So since there are 4 right next to it, then it has an additional 4 atoms. And then this makes for, rather than 4, it has 8 electrons in its outer valence shell. Now, 4 of them are what we call covalent bonds because they are a shared electron. So, and then as we go on, we could have others out here, and what we would find is that all of them would have the 8 electrons, except those that are on the very outer edge, and then they wouldn't have the advantage of having that the extra electrons. Okay, electron distribution. Let's consider the distribution of electrons at 2 temperatures. And you have a text in your, or a picture in your textbook that you might want to refer to this. I did not have access to that picture, so I couldn't put it into my presentation. But we're going to consider how these electrons are distributed at absolute zero and at room temperature. Now, at absolute zero, electrons are at their lowest energy level. Material acts like an insulator because no energy and no electron flow or movement. And there are no electrons in the conduction band. Now, you would kind of figure that this would be the way it would be with a semiconductor, because remember we looked at, on the previous screen, we looked at the structure, and we saw that there were 8 electrons in that valence shell. This is a rather tightly bound structure, but at absolute zero, there's no energy, and so the possibility of one of these electrons becoming free and becoming what we would call a conduction band electron is just virtually impossible, because at absolute zero, there's no extra energy, and so it's going to stay in this tightly bound state. Now, at room temperature, valence electrons have absorbed enough energy to move into the conduction band. At room temperature, a valence electron can receive enough energy to break away and move to the conduction band. So, at room temperature, okay, there is energy that's being picked up by these electrons, and one of these electrons can actually move out of this valence band and become a free electron. Atoms with broken covalent bonds, missing an electron. Now this one right here, this broken, it's missing an electron right here. They have a hole present where the electron was. And this is a concept we have not talked about before, but here we have this piece of silicon atom. It had an electron right here. That electron moved out to become a free electron, and what is in its place is, we call that a hole. Now there's nothing there. It's a hole. This simply means that it is a vacant spot where an electron was. For every electron in the conduction band, there is a hole in the valence band, and they are called electron-hole pairs. And so one concept that we will see here is that in pure silicon, you'll have an equal number of free electrons as you have holes, and that just kind of makes sense. Okay, electron distribution. As more energy is applied to a semiconductor, more electrons will move into the conduction band, and current will flow more easily through the material. Therefore, the resistance of an intrinsic semiconductor material decreases with increasing temperature. Now, that's an interesting thing. The resistance of an intrinsic semiconductor material decreases with increasing temperature, and the reason is the more heat, the more electrons that are free. And this is referred to as a negative temperature coefficient. As the temperature goes up, the resistance goes down. Okay, this concludes our introduction to semiconductors, and specifically to intrinsic semiconductor devices.